Welcome back. This time we are going to look at the law of sines. We're getting awful fancy sounding getting into laws, but really it's not that fancy once you get used to what we're doing with it. Let's get right into it. So far, in this unit, we have been dealing with right triangles. All the triangles we've been looking at or drawing or inscribing have always had some right angle to it. And because we did have right triangles, we got all of these nice properties to follow up with. We had, well, first of all, for any triangle, the interior angles always sum up to be 180 degrees. That is always the case. Also the case with right triangles, of course, but in general too. Also true in general is what's sometimes referred to as the triangle inequality. The longest side of a triangle cannot exceed the sum of the two smaller sides. That is a hilarious typo right there. I'll get that fixed. The sum of the two smaller sides has to be greater than or equal to the largest side. That's just a property, a geometric property of triangles. It has to be that way. Now, two things that we get for having a right triangle. First thing we get is the Pythagorean theorem. A squared plus b squared makes c squared, where c is the hypotenuse, a and b are the other two sides. And also, as we've been looking at in this unit, the trigonometric ratios as well are also defined for right triangles. Sine of an angle, so angle theta up here is opposite over hypotenuse. Cosine of that angle is adjacent over hypotenuse. Tangent's opposite over adjacent, SOHCAHTOA. Those are the ratios of the side lengths. And the ratios, no matter how big this triangle is, for the same angle theta, the ratios will stay the same. But all that has been true for right triangles. And there are plenty of triangles out there that are not right triangles. So what can we say about those guys? And this is generally how they're drawn. This is kind of embarrassing that they didn't do the correct... whoever I stole this from did not do the correct convention. Angle C here, lowercase c should be here. They got A right, A to A, but big B here should go to little b on the opposite. At any rate, though, in the instance that you're working with something not a right triangle, if you're working with a general triangle, if you don't even know you have a right triangle, then you cannot get a few things. In particular, you cannot get the Pythagorean theorem, and you don't get any of the trigonometric ratios. Because let me tell you this, there is a triangle out there where there's two sides of length 2, and the remaining side is of length 3. That is not a right triangle. That does not satisfy the Pythagorean theorem. Right? 2 squared plus 2 squared does not equal 3 squared, which is 9. You don't get the Pythagorean theorem in general. And yes, there is such a triangle. This is not an impossible construction. I have made it for you here. So this is 0 to 3, and up here is 0 to 1.5, comma, root 7 over 3. So picked because if you did the distance formula from here to here, you would have a distance 2. If you did the distance from here to here, you'd have distance 2. And from here to here is obviously distance of 3. So yes, there are such triangles, and no, the trigonometric ratios and the Pythagorean theorem no longer, well, they just don't apply anymore. I forget if I said too many no's there. You don't get that anymore. In fact, if you don't have a right triangle, or even if you don't have the guarantee of a right triangle, you cannot use the Pythagorean theorem. Period. Full stop. So what can we use? Obviously, we can still use the fact that interior angles sum up to 180 degrees. We still have a triangle. We still have a triangle, so we still have the triangle inequality. But that's all we got. This other nice stuff that we can use to definitively solve for dimensions of triangles, we no longer have that. We've got to do something else. And here's our something else. We want to do something so as for a general triangle, ABC, we want to use as few of these values as possible. I think it needs 3 of them. We need at least 3 of angle A, angle B, angle C, side A, side B, side C. We need 3 of those, and we need hopefully any 3 of those, and use that to solve for all of the rest. And as you see here, the way to do that is to start by admitting that we don't have a right triangle, but optimistically, we recognize we can draw right triangles within our triangle. So there's triangle ABC, and this time the convention was correct, A to A, B to B, C to C. And if we drop what's called an altitude, if we drop this vertical line so that it's perpendicular with side A here, if we drop this altitude, we form not one, but two right triangles. First of all is ABD, the other is ACD. And what we've got now, right angle here, angle B is unchanged, angle C is unchanged. So for triangle ABD, we can use the unchanged angle here, the unchanged side length here, C, and use this new value, H, and make a trig ratio that establishes that sine of B is equal to H over C, and that sine of C is equal to H over B. And those things together, right, if we were then to solve for our H in terms of everything else, we would have H equals C sine B, and H equals B sine C. So rewriting that in maybe a more comfortable and familiar thing, we have the ratio of any side length to any sine of the opposite angle is preserved. It's always equal for every triangle period. You pick any angle, you take the sine of that thing, you cut that into the length of the opposite side, and no matter which guy you pick for any triangle, those ratios are all equal for every triangle. Now wait a minute, you say. You're not happy with this, because I've only done it for B to C, and also I've only done it for this very particular triangle construction. What if I had an obtuse triangle, you say? Well, that's very observant. And for you, I will point this out. We can still work with obtuse triangles. So if we have an obtuse angle here, we'll still drop an altitude. It does extend beyond the reach of my triangle, but we're going to still be okay. I still have triangle ABD, so I can still use sine of angle B is H over C. I still have that one. But now I can't use sine of C. Instead, I have to use sine of 180 degrees minus C. I have to use this supplement in here to worry about triangle ACD. But the sine of any angle is equal to the sine of the supplement. So the sine of the supplement of C, being H over B, is now equal to the sine of C, which is H over B. And so once again, under this construction as well, we still have the case that the ratio of two sides to their opposite angles, well, the sine of their opposite angles, we have the ratio being equal. Well, wait a minute again, you exclaim. You have it for B to B and for C to C. Well, how does the other side come into the mix, right? Triangles, last time I checked, have three sides, so we still have more to do. Okay, I admit that. But all you have to do is just draw another altitude from C to C, maybe, and just do it again for angle B and angle A. Drop another altitude from C to C. Do the same steps again for angle A and angle B now, and you will eventually work A to sine A into the mix. And so if A over sine A equals B over sine B, and if B over sine B equals C over sine C, then by the transitive property, all three of these ratios are always equal for every triangle. That is the law of sines. The ratio of any side length to the sine of its opposite angle for every triangle is always equal. This is true in particular for right triangles, but it is true in general for every triangle. And I admit what we've just looked at here with this construction is a bit daunting. That's why I walked you through it. I want you to see visually that the law of sines comes about by using the right triangle trigonometry approach. But now, in having done the hard stuff, having done the hard part, having reached this point, in the next few videos we will look at reaping the rewards and being able to identify unknown dimensions for still more complicated triangles than just plain old right triangles. So I look to see you in those videos. I think I'll have a quick question for you right now. Take a break, let this set sink in, and we will come to appreciate these formulas, these equations, in the coming videos. See you then.